Júlio, bom dia.
Tá me ouvindo também?
Tô ouvindo sim. Você ainda está configurado, né?
Não, já
Sim.
configurei tudo, só não deixei entrar ainda, porque não tá na hora.
Beleza, porque só ia dizer que estava indo para a página da Telnet.
Não, mas vai pra página da Natonet mesmo. Eu já comecei o stream lá, já deve estar aparecendo lá o listado. Porque esse aqui é público, deve estar lá.
Tranquilo.
Ô, Bruno, tá aí?
E aí, pessoal, bom dia, tudo bem? Vocês me escutam?
Sim.
Bom
Bruno,
dia.
a gente, na hora da abertura, a gente pode deixar Danfrey de host. Fica eu e você mesmo sem. A gente não precisa trocar, não, naquela hora, ficar. Só na hora da apresentação do Keynote, aí você pode ficar de host, mas depois, Danfrey fez o treinamento de host, ele consegue fazer tudo.
Ah, então beleza. Então, como você vai fazer então? Você vai deslogar e logar na sua conta e aí
Vou, vou
automaticamente,
deixar ele, vou deixar ele de host e vou deslogar e logar na minha conta pessoal.
aí eu entro, assim que você sair, eu entro para ficar como backup de Dumfries, né?
Então, não, quando você, logo no começo do Keynote, você pode logar com a conta do Lars, aí eu saio, né, logo com a minha conta pessoal, e aí vocês trocam aí host com host para deixar a pessoa certa.
Não, então, eu faço isso de logar depois que você sair e que Dumfries assumir, porque aí eu sei que eu sou o próximo da
Isso,
fila, digamos assim.
isso, isso.
Beleza.
Então eu tenho que
É,
sair também, né?
não, você não precisa sair não, pode ficar aí.
Beleza.
Pode ficar aí.
É que você é o próximo da fila, né? Ó, renomeia aí vocês dois, porque daí a galera sabe quem é quem, né? Porque os dois com o mesmo login, aí ninguém sabe
Sim,
quem é
eu
quem.
vou colocar.
Coloca o nome pessoal mesmo?
Eu vou botar o pessoal, Júlio.
Ok.
Eu baixei os vídeos, o vídeo dessa primeira apresentação tá bem baixinho. Pelo
Teve
menos.
alguns vídeos que eu dei play ontem com o pessoal que eu vi que estava baixo, mas o meu fone é baixo. Aí a
Mas,
LM disse que estava ok, então deixa
mas no
aqui.
YouTube tá baixo também. Mas, se bem que eu coloquei o Day Play pela caixa de som aqui do computador, né? Então pode ser que tenha ficado baixo por causa disso também. Dá uma olhada, Bruno, se tá listando o vídeo lá no Natalnet. Eu já comecei o stream há algum tempo.
Então quer dizer que a gente está.
Essa conversa da gente aqui saiu lá no stream.
É isso, né? A
Sim,
conversa da
sim,
gente está indo para
sim, sim.
o YouTube, né?
Tá.
Já tá confirmei aqui, já tá tudo certo.
Tá.
É muito legal isso.
No caso desses vídeos aí, como eu tô como host, como será? Um vídeo das
Não, não,
apresentações.
não tem nenhum problema, não. Você não vai ter algum problema com isso.
Tá, no
Porque não
caso,
vai ter nenhum vídeo
o
para tocar
co-host
quando.
que vai tocar, né?
No caso, quando você tiver como host, você não vai precisar tocar nada, não. É porque na abertura, todo mundo que é da organização vai tá alocado, né? Vai estar como.
Sem problemas.
Aí, nesse caso aí é mais tranquilo, né? A gente apresenta aí.
Tá, só para ficar claro, eu vou ficar como host na abertura e quando terminar a abertura, no caso, eu vou sair para Bruno assumir como host, é isso?
Não, não, não. Tá, a gente combina, mas assim, basicamente na abertura você vai ser o host. Eu e Bruno vamos
Sem
ficar sem,
problema.
sem, vamos ficar sem ser host,
Na
que a
Tá
gente tá
bom.
na
abertura ou
organização.
no Keynote só?
No Keynote a gente faz do jeito que a gente combinou, Bruno.
Tá.
Tá, então eu vou começar a deixar o pessoal entrar. é, e aí a gente, aos poucos, vai organizando aqui, pessoal. Eu vou ficar mudo.
Bom dia a todos, me escutam?
Bom dia.
Bom
Sim,
dia,
estou
Vinícius.
escutando.
Ah, que bom. Só para... os autores estão presentes, quem vai apresentar, ou cada um dos artigos?
Bom, eu sou do artigo de 915, estou aqui já.
E a Lara, né?
Isso.
Isso, Lara. O Carlos não está aqui ainda, né? Alguém do primeiro trabalho? Agora, o Eduardo aqui.
Bom dia,
Bom dia, Eduardo, tudo bem?
tudo bem.
Vamos guardar uns 2 minutinhos aqui para ver se o primeiro
Bom dia
autor...
a todos.
Bom dia, cara, tudo bem?
Bem, Vinícius. Bom dia, professor Todd.
Bom dia, uma satisfação vê-los por aí. Só lembro, vale a pena ver se não entra ninguém de fora aí no meeting, aí tem que ser em inglês, mas por enquanto é todo mundo brasileiro que está aqui. Até por exemplo, os keynote speakers, eu falei eu dei o link das palestras, de repente alguém aparece aí, a gente tem que estar um pouco atento a isso aí.
Sim.
Ah, sim, obrigado, professor.
Nueve horas.
Vamos ver quem mais nós temos aqui. Maria Cornejo, do primeiro artigo, né?
Good morning.
Hi, how are you, Maria? Maria, do you present the first paper?
Yeah, I'm going to present the paper. I sent a video, and I think it's better to respond the
Okay, we use the video, but first I would like to welcome everyone to the first session of the 18th IEEE Latin American Robotics Symposium, 19th Brazilian Symposium of Robotics. This is our technical session, Assistive Robotics and Human-Robot Interaction, the first section of this topic. Later of this section, we have the opening ceremony, and I hope to see everyone in this ceremony. Can we start with the first video?
Sorry,
Great.
I can hear you. Hello everyone, my name is Maria Cornejo Lupa, and I'm going to talk about our paper, a strategy to validate knowledge representation in service robots through experimentation applied to the Slam domain. Hello everyone, my name is Maria Cornejo Lupa, and I'm going to talk about our paper, a strategy to validate knowledge representation in service robots through experimentation applied to the Slam domain. Semantic knowledge is being introduced in robotics. It is used to complete the information of maps with semantic information about locations and objects, among others, in the so-called semantic mapping field. Ontologies are a widely used tool for modeling and formalizing semantic knowledge, but like every approach or tool, ontologies must be evaluated to determine if the ontology suits the problem. A common way to evaluate ontologies is by using a formal comparison and evaluation, focused in the quality and correctness of the ontologies and their ability of modeling the domain, considering features at the lexical and structural level. However, these strategies neglect the empirical evaluation in terms of the ontology's performance in robotics experiments. In this sense, we propose a novel approach that takes advantage of existing approaches to combine several strategies and standardize how researchers and robotics practitioners can validate a knowledge representation through experimentation. We propose three different experiment sets: validation of robot performance correctness in different scenarios, user validation of the quality of the knowledge representation, and measure of inference response time. The first experiment set, validation of robot performance correctness in different scenarios, we evaluate the robot performance correctness by comparing maps built by robots performing a traditional Slam algorithm versus a map reconstructed with OntoSlam ontology. We follow the next steps. Robot A performs the G-mapping algorithm using the data structures of rows. The resulting map is considered as the correct one. The same robot translates the Slam information to instance of the OntoSlam ontology. The resulting map is represented in triplets and stored in a web repository. Then, a robot B recovers reconstructed maps and other information directly from the ontology instance. Finally, we compare that both representations have the same mapping information. For the next experiment, user validation of the quality of the knowledge representation. In some cases, it is not possible to have algorithms to which compare the responses of the robots. For example, we don't have a benchmark result. In such cases, the option is to survey expert users about the robot's behavior. That's why a set of tests was designed to allow the user to verify the quality of the knowledge representation. It could be through visual evaluation, surveys, interviews, among others. The third experiment set, measure of inference response time. Since service robots have time constraints in order to produce responses in real time, one validation experiment commonly used is related to measure the time the robot delays to reply a stimulus and convert it into actions. In this sense, a set of tests to measure such as response time should be integrated into the validation. This measure might be taken from the moment the robot receives the stimulus to the moment the robot performs the specific action, which includes the time of accessing the information needed at the semantic repository. To demonstrate the suitability of the proposed strategy, we evaluate onto Slam, an ontology in the Slam domain, consisting of robot information, environment information, temporal and workspace information. It incorporates the information related to the time and the uncertainty of the robot positions and landmarks. With this ontology, we perform experiments on different maps with Robotic Operating System, known as ROS, and Gazebo Simulator, with two social robots with different characteristics, the Turtlebot robot and the Pepper robot. For the first experiment sets, validation of correctness, we elaborate a set of queries to verify the information that a robot needs to fulfill the objective of Slam. This knowledge is related to robot information and map information. To answer the queries with Slam, we use SparkQL and C++ scripts to access ROS data. We mainly consult ROS topics, like in this case, we consult the topic of odometry of the ROS. We took the pose, the position, and the x, y, and z coordinates. And in the case of Slam, we do this SparkQL query, where we query about Cartesian x, y, and z, and we have this answer, which relate the position, the pose-based footprint, with each Cartesian x, y, and z. For the experiment sets to validation of quality, we choose the visually validation. We can see these maps, which are the result of the constructed mapping onto Slam, with the original environment simulated on Gazebo, and the correct one constructed by G-mapping algorithm are the same. We can appreciate that the generated maps based on the Slam represent correctly the shape of the room and the landmarks, presence, and position. Those are the experiments performed on the Turtlebot 3 robot. For the experiments on Pepper, we can see the same behavior in larger environments and with people as landmarks. For the third experiment set, inference response time, we can see here the time in milliseconds spent executing queries with both techniques onto Slam and ROS. For the robot information questionnaire, as shown in the figure, onto Slam is able to answer all the queries, unlike ROS, which could not answer query 2. As expected, querying onto Slam is noticeably slower than querying the ROS topic directly. However, the performance of both techniques is good in terms of time, as no query exceeds the 10 milliseconds. For the second questionnaire, the map information questionnaire, which we measure this chart in seconds, the result is different, since onto Slam is not only faster, but also is able to answer questions that ROS itself cannot, as question 8 and 13. As shown in this figure, the reason why onto Slam is faster in this questionnaire is because while ROS has to go through 100% of the cells of the message in the topic map, onto Slam only goes through the triplets that correspond to the scanned cells of the map. That is to say, without considering all the cells marked as unknown, and which constitute more than 70.5% of the map. The result of this work show that our proposed validation strategy is well suited for testing and making experimental validation of ontologies in the robotics field. From the result, we can conclude that no information is lost in the face of instantiating onto Slam with respect to ROS. The execution time of the queries in onto Slam is longer than ROS. Nevertheless, the ontology models information that ROS can't. ROS topics can only be performing during the time the robot is navigating while solving the Slam problem. With an ontology, it is possible to keep records of all necessary information that can be consulted as many times as required. In conclusions, we propose a novel strategy to evaluate ontologies through experimentation, emphasizing correctness of response, user evaluation, and execution time. To demonstrate the suitability of the proposed strategy, we applied our validation approach to validate onto Slam, obtaining results that show the benefit of including the semantic web without compromising the information for robotics application. Thank you very much for your attention. If you have any questions, you can do it now or contact us via email.
Okay, thank you, Maria, for the presentation you show us. Anyone, any questions, any doubts about this work? You can write on the chat or open your microphone and ask. Maria, I have one question for you. You are developing this first onto Slam, and what is the difference, or if there is similar systems from these using the ontology onto the system LARS or other system you have? Could you show me where this system you propose is in the literature, in the technical systems you have now, the tools we have at this moment? How is inserted your system, your proposal? What advantages, what facilities it proposes?
Okay, thank you, Vinicius. If I understand correctly the question, you ask about where is the place of the onto-Slam ontology in the old technology flow of doing Slam or robotics application. Am I right?
Yes.
Yeah, okay. It's exactly after the robot performs the Slam and storing that map, instead of storing a set of cells marking, I don't know, in 1 for probably places where there are objects and 0 where there are no objects, instead of doing that, and instead of, I don't know, saving in one file for one room and one file for another map, and that, we use the ontology to construct a graph of triplets where you can, in the future, or not in the future, it could be at the same time in another robot, but you can have the information all related. Like for the questions that Ross cannot respond, we have a benefit for the semantic web or the onto-Slam ontology, because the ontology that gave us the relative information, like there is something closer, close to the robot or to the left to the robot, and I don't know, behind the robot, and relative positions information, not only the uncertainty information. Other benefit of using the proposal is that during the Slam, you have to, if you have a query in a specific time, you have to perform the Slam or redo all the mapping process. But with the onto Slam, you can query the graph that is constructed, and you can query every time you want or any time you want.
Okay, understand better now, Maria. We have any more questions? No more questions. Okay, thank you very much, Maria, for your work. It's very interesting, very important to the advancing ontology. So I think I desire you a successful development of this OntoSlam tool. Do you have the next? Lara is here.
Bom dia a todos, estou aqui já.
Okay. Lara, do you prefer to present yourself or use the video uploaded?
Pode utilizar o vídeo mesmo.
Okay, we prepare it.
Olá a todos, meu nome é Lara Toledo Cordeiro Ottoni, sou aluna de doutorado do Programa de Pós-Graduação em Engenharia Elétrica da UFBA e venho apresentar o nosso trabalho que tem como título A Review of Emotion in Human Robotic Interaction. Esse trabalho foi realizado em conjunto com o professor Jess. Bom, aqui está o sumário, os tópicos da nossa apresentação. Primeiro irei falar sobre a introdução do tema, em seguida irei apresentar a metodologia que foi utilizada para selecionar os artigos que fizeram parte da revisão de literatura. Posteriormente irei falar sobre Affective Robotic Human Interaction. Em seguida irei fazer uma discussão dos resultados e por fim concluir a apresentação. Bom, a robótica social ela é uma sub-área da robótica que tem ganhado uma importante visibilidade nos dias atuais. Essa visibilidade se dá por conta de desenvolvimento de tecnologias que melhoram a qualidade de vida das pessoas. Na robótica social é realizada a interação humano-robô. Essa interação se dá por meio de fala, gestos, expressões faciais e outras formas. Uma abordagem que vem crescendo dentro da interação humano-robô é a utilização de emoções. Assim como na interação humano-humano, a gente utiliza de emoções para se comunicar, seja através das expressões faciais, através da emoção pela voz ou através de gestos. Na interação humano-robô é importante a utilização de emoções para que o humano se sinta confortável, fazendo uma interação o mais natural possível. Com isso, é importante que o robô seja capaz de, além de reconhecer a emoção do humano, seja também capaz de transmitir emoções. Portanto, esse artigo ele tem como objetivo investigar como que a literatura tem abordado a utilização de emoções na interação humano-robô. Aqui a gente tem um fluxograma que apresenta como que foi selecionado os artigos. Primeiro, foi utilizado a base de dados da Scopus. Foram utilizadas as seguintes palavras-chave: Human Robotic Interaction and Emotion. Foi utilizado o filtro Document Type e selecionado apenas os artigos. Com isso, foram selecionados 3 revistas para participar da nossa revisão de literatura. Seguindo aquele fluxograma, foram coletados 72 artigos, 45 da International Journal of Social Robotics, 14 da International Journal of Advanced Robotic Systems e 13 artigos da I3E Access. A leitura desses artigos foi voltada para responder à pergunta: como a literatura tem abordado a utilização de emoções na interação humano-robô? Respondendo àquela pergunta, a gente tem que a literatura ela tem apresentado 2 caminhos na utilização de emoções para a interação humano-robô. O primeiro caminho são métodos que fazem com que o robô reconheça a emoção em humanos. E o segundo caminho são técnicas que fazem com que o robô seja capaz de transmitir emoções. Vamos falar um pouquinho aí de cada um desses dois caminhos. No primeiro, que é o método para detectar emoções em humanos, são abordados de algumas formas, como, por exemplo, detectar emoções em humanos a partir da expressão facial, a partir da fala, a partir do toque e também a partir dos sinais fisiológicos. Essa parte de detectar emoções em humanos é extremamente importante para que o robô seja eficiente em atualizar as suas ações de acordo com a emoção em que o humano em que ele está interagindo está expressando. Então, ele atualiza, ele muda a sua abordagem de acordo com a emoção do humano. O segundo caminho, que é a emoção do robô, o robô expressar emoções, essa emoção ela pode ser expressada de algumas formas, como, por exemplo, através das expressões faciais, através da linguagem corporal, através da fala e através também da aparência. E como a gente falou anteriormente, a demonstração de emoção do robô é importante na interação humano-robô para que o humano se sinta de uma forma amigável, de uma forma natural, essa interação. Aqui a gente vai falar um pouco sobre as emoções do robô, a começar da expressão facial. Então aqui a gente tem dois exemplos nessa figura. O primeiro robô é o robô Sam e o segundo é o robô Probo. Os dois estão expressando emoções através da expressão facial. Eles estão expressando as 6 emoções básicas, que são alegria, tristeza, raiva, medo, surpresa e desgosto. Então essas são as expressões em que o robô Sam e o robô Probo estão expressando através da expressão facial. Tem também através da linguagem corporal. Então o robô ele pode demonstrar emoções através da linguagem corporal, como por exemplo, através do movimento com as mãos, através da forma em que ele anda, através também da inclinação com a cabeça. Então aqui a gente tem no primeiro exemplo o robô Robovia X e o robô Brian. Os dois trabalhos são voltados para fazer com que o robô transmita emoção através da linguagem corporal. Tem também a forma de o robô transmitir emoções através da fala, né? Eliminar aquela voz robotizada em que a gente conhece e transmitir emoções. Isso faz com que o robô apareça mais amigável para o humano. Então aqui eu trouxe 2 trabalhos. O primeiro é o robô Health Board, que interage com pacientes de um hospital. E nesse trabalho eles investigam qual é a voz em que o robô emite, que faz com que os pacientes se sintam mais empáticos com esse robô. No segundo trabalho é incorporado um estudo em que ele incorpora, né, informações da psicologia, neurociência e da interação humano-computador na voz do robô. Tem também trabalhos em que mostram a emoção do robô através da aparência dele. Estudos mostram que a aparência do robô ela afeta diretamente na interação humano-robô. Eu trouxe aqui um exemplo pra gente em que é realizada uma pesquisa das preferências dos estudantes universitários com relação à aparência desse robô. E como resultado, os estudantes universitários eles preferem interagir com robôs que sejam parecidos com humanos, ou seja, robôs humanoides. Além disso, eles gostariam que o robô seja capaz de falar, se comunicar e que expressasse emoções positivas. Então aqui na figura 3, a gente tem um esboço dessas preferências dos estudantes universitários. Com isso, a gente chega na discussão do nosso trabalho. Aqui tem um gráfico em que mostra a porcentagem dos trabalhos que foram avaliados. Então, 70% desses trabalhos avaliados buscam incluir emoções em humanos, fazendo com que o robô demonstre emoções. E 30% dos trabalhos são voltados para que o robô detecte, reconheça emoções em humanos. A partir disso, a gente pode verificar uma forte tendência dos artigos da literatura em estudar modos do robô transmitir emoções e principalmente através das expressões faciais. Estudos que buscam fazer com que o robô transmita emoções através de gestos e através da fala são áreas que ainda têm poucos artigos e tendem a se desenvolver no futuro. Também é verificada uma forte tendência nos trabalhos em que buscam melhorar a aparência do robô, fazendo com que esse robô agrade mais os humanos em que ele vai interagir. Bom, é verificado também algumas lacunas na literatura, né, que podem vir a ser trabalhos futuros, como, por exemplo, a partir da metodologia utilizada, não foram encontrados artigos em que realizam a detecção de emoção humana através da linguagem corporal, como, por exemplo, através de gestos, movimento com as mãos, a forma de andar. Também é observado que muitos dos artigos são protótipos, ou seja, são apresentados os módulos, apenas módulos de reconhecimento, ou então do robô mostrar emoções, mas o robô não está pronto de fato. Também é verificado em que alguns dos trabalhos, o robô tem apenas uma habilidade, ou ele reconhece emoção, ou ele expressa emoção. Então, é verificado essas lacunas na literatura. Como conclusão do nosso trabalho, a gente teve aqui como objetivo responder à pergunta como a literatura tem utilizado a emoção na interação humano-robô, e como resposta a gente tem dois caminhos. O primeiro é a forma de reconhecer emoções em humanos, e no segundo caminho a gente tem a forma de inserir emoções nos robôs. Com isso, a gente observa, a gente percebe a importância da utilização das emoções na interação humano-robô. Bom, obrigada a todos, estou disponível para as dúvidas e segue meu e-mail também para qualquer dúvida.
Thank you very much, Lara. If you have any questions, you can raise your hand. You have a button, an icon to raise the hand. Okay, Maria, do you have a question?
Yes, thank you. Thank you, Lara, for the presentation. I have two questions. In the first part, you said robots can recognize emotions through speak and corporal gestures, and you said physical signs, and I want to know what physical signs do you find in your research? And that's the first one. And the second one, it's about the appearance of the robot. It's only the shape of the robot, like it's a humanoid robot or other form of the robot, or what else's options do you find in your research about the appearance of the robot? Because I'm working with a humanoid robot Pepper, and I don't know, we try to we think we can dress up the robot for being more friendly, but it is just only, it is not correct because of the ventilation of the robot, and I don't know, it cannot be done to dress the robot. But what else you can recommend me for improve this appearance? Thank you.
Can I complete the question, Lara, please? I think you have done a very nice state of the art, and I wish if you have some physical implementation of this already done. That's I think with this you can complete these three answers. Thank you.
Obrigada a todos. Vou pedir o share da sessão. Vinícius, você pode me ajudar com o inglês, por favor?
Well, I was not paying attention to the question. Sorry, Maria. I believe that Maria wants to know physical science. You have aspectos físicos, né, que tu tenhas identificado que sejam importantes. Eu não peguei a segunda parte da pergunta dela. Maria, please, could you repeat briefly your question?
A segunda parte é sobre aspectos implementacionais do robô em si. Se você, qual tipo, é por isso que eu perguntei a minha logo em sequência, junto, né? Qual é o tipo de robô que você está utilizando, como é que fica a estrutura, a altura desse robô, para você dizer se isso influencia também nos aspectos aí de interação.
Bom, com relação à altura do robô, é isso?
Também.
Aspectos físicos, né?
Forma, aspectos físicos, forma.
Então, eu percebi que teve uma tendência muito grande na literatura de demonstrar a aparência do robô, né? De fato, a aparência do robô influencia bastante na emoção em que aquilo causa no humano. Então, com relação à altura, é extremamente importante, né? Eu já vi relatos de que o robô ele não pode ser maior que a pessoa em que ele está interagindo, porque isso, né, causaria medo na pessoa. Então, a altura em que o robô com certeza é um fato relevante para com que a pessoa se sinta à vontade em interagir com aquele robô. Aspectos físicos variam muito, então, nesse mesmo estudo, eu vi um trabalho, né, com relação à aparência, em que é feito da mesma forma em que foi feito voltado para as preferências dos estudantes universitários, foi feito também um estudo voltado para as preferências dos idosos. Então, ao contrário dos estudantes universitários que preferem robôs com aparência parecida com humano, né, ou seja, robôs humanoides, os idosos, eles preferem robôs que sejam diferentes da aparência humana. Então, a gente percebe que cada segmento, cada grupo, tem que ser feita uma pesquisa para verificar qual é a aparência em que aquele grupo em que você está querendo fazer a interação com o seu robô, ele gostaria que o robô tivesse uma certa aparência. Respondido a pergunta?
Isso, agora só faltou a minha parte. Vocês já estão implementando isso aí, né, na UFBA?
Então, esse foi um estudo preliminar. A gente já tem um robô implementado, né, que está em desenvolvimento aqui na UFBA, chama Highbot. Ele é voltado para a interação humano-robô com crianças autistas. Então, a gente, né, utilizou desse grupo para poder fazer essa implementação da aparência do robô.
Thanks.
We have any questions? If not, I have some questions to Lara. Well, I will pose my questions. Lara, nesse estudo que tu fez da parte de emoções, né, identificação de emoções, eles eram simplesmente em situações de interação social apenas, ou tu conseguiu identificar algum padrão mais específico de emoções quando está fazendo uma tentativa de um processo de reabilitação, alguma coisa em termos de reabilitação física, de tratamento, como, por exemplo, comentaste aí na questão de interação com autistas, né? Isso muda do caso de uma mera interação social, de um robô atendente, um robô que está interagindo em algum momento, ou não tem diferença essas interações? Conseguisse identificar alguma coisa disso?
Você fala no caso de reabilitação, né? No caso da pessoa estar ali precisando de alguma ajuda, é isso?
Isso, de ter alguma interação com objetivo de recuperação, seja física, de tratamento de autismo, enfim, de alguma
Certo.
questão, ou uma mera interação de um robô num shopping, com pessoas andando, enfim.
Aham. Esse estudo que eu fiz, ele engloba, eu consegui perceber essas duas partes que você falou, certo? É feito um estudo com pessoas, né? Igual você falou, em shoppings, em teatros, também em laboratórios, entre robôs e pessoas jogando um jogo, né? Interações simples, assim. E também é realizado, sim, estudos que são voltados, sim, para a reabilitação. Tem esse trabalho do robô HealthBot que eles fazem o estudo da voz do robô ser mais empática, que é um robô que interage com pacientes em um hospital, e ele oferece remédios, e ele lembra a pessoa de tomar os seus remédios, e afere a pressão arterial. Então, ele é um robô que é feito esse estudo dele ser mais empático com essas pessoas que estão passando por um momento difícil, né, em suas vidas, e para ele ser ali o mais amigável possível com relação à voz dele, né? Ser tratada a voz dele para que essa voz seja o mais empática possível com aquela pessoa. Além dos estudos que tem também, muitos estudos que trabalham com crianças autistas, e eles mostram, né, o quão eficiente é a utilização da emoção para tratar, ajudar, né, os terapeutas e professores em se comunicar com essas crianças autistas. Respondido?
Obrigado. Claro, obrigado, Lara. Obrigado pela
De
tua...
nada, obrigada a todos.
Well, the next Carlos Magrin.
Hi, good morning.
Carlos, do you prefer to present yourself or to use the uploaded video?
Use the video.
Okay, we are loading now.
Hello, I am Carlos Eduardo Magrin.
Just a few
I'm going to
seconds.
present the work Creation a Digital Twin as an open source learning tool for mobile robotics. The other authors of the paper are Gustavo Del Conte and Eduardo Todi. So, there are many solutions for learning mobile robotics, such as PR2, Fetch, Turtlebot, KukaUBot, Husky, and Pioneer 3DX. However, to encourage undergraduate students to explore the behavior of a mobile robot at different levels of learning by developing a mobile robotics platform. An optimized design can meet several stages of knowledge and involve additional skills related to mechanics, electronics, and programming. The digital twin concept has been widely applied in industrial application fields, such as smart manufacturing, the same shows the picture, aerospace, automotive, city management, and agriculture. Based on the digital twin concept, Tao considers it as an efficient way to realize the fusion between physical and virtual environment, and represents the next surge of digitalization. So, the relevance of digital twin concept is emphasized by academia and industry, related by the cyber-physical systems, and none of the challenges for Industry 4.0, connecting the physical and virtual environment. So the traditional three-dimensional digital twin proposed by Greaves attends the basics of creation a real mobile robot model in a virtual environment using physical space, virtual space, and connection. Here, Tao proposes a five-dimensional near digital twin shop floor conceptual model, including physical part, virtual part, connection, data, and service. We used the concept with a full 5-dimensional digital twin for proposing the digital twin mobile robot. Our digital twin mobile robot concept model using physical system, real mobile robot, virtual system, robot model in a simulator platform, service, integration between the host nodes, data, exchange host message by topics, and connection, data exchanging cyber-physical systems through the host master. Creation. The 2P4WD was modeling Copilha Sim using CAD model, designing CATIA software, export STL file to URDF format, and describing our robot elements in XML file. Figure shows mount on the top of the mobile robot, 80 sonars, Kinect, and Hokuyu laser scanner. So, was used the floor plan the PNU campus at the University of Curitiba for modeling indoor and outdoor virtual environment. The top figure was create scene using infrastructure available in the Copilha Sim, such as walls, floors, and doors. In Digital Twin Mobile Robot, figure shows the virtual and physical digital twin mobile robot, developed to apply multi-sensors and move around in the environment. The design helps to include and adjust many types of sensors. Here, figure shows simulation 2P4WD model locomotion and perception. Perception in indoor environment using laser scanner, diff image, RGB image from Kinect. Here, figure shows laser scanning the scene, Kinect showing edge detector output, 8 sonar reading distance, and robot orientation. The process of developing a digital twin mobile robot has allowed the students to learn in many different levels of knowledge, engineering fields, as follows: space for learning mechanics, research about material science, manufacturing process, and development of a mechanical CAD, CAN project. In space for learning electronics, research about different sensors using mobile robotics, development and electronic circuit, power and or control, and print circuit board layout. And programming microcontroller implementation low-level functions, such as sensors read, motors control, and communication. Space for learning computer science, creating a virtual system of the mobile robot platform, development of a script to integrate the virtual system and physical system using host framework, and develop the algorithm for exploring autonomous mobile robots tasks, such as locomotion, perception, localization, and navigation. The contribution for our work provides a learning tool for mobile robotics using the digital twin mobile robot concept to encourage students in research to model, simulation, assembling, and programming their own mobile robots. Collecting multi-sensor data for creating a dataset exploring indoor and outdoor environments on the campus of the University of Curitiba complements the approach of using the digital twin mobile robot as a learning tool for autonomous mobile robots, leaving it as a guideline for future work. D2P for WG Digital Twin Mobile Robot is an open source project and will be available in GitHub. So that's it. Thank you. Thanks for watching. Do you have any questions?
Thank you very much, Carlos, for your presentation, your presence here. Anyone can raise the hand or write in the chat some questions.
Maria,
Nobody?
Thank you, Carlos. I have a little question. You said about your development of algorithms of localization and navigation. What are the algorithms that you already implemented or plan to implement?
Thank you, Maria. For behavior, the mobile robots implement this LAN with the mapping, using perception edge detector.
Thank you. And you have any algorithm for path planning? I don't know.
Algorithm for what? Sorry.
For path planning.
Path planning.
Yeah.
Just using the mapping for behavior, the mobile robot.
Okay. Thank you, Carlos.
Welcome.
Carlos, from YouTube, Victor Sabino asked, did you use encoders, IMU, or other sensors for low-level control of the robot in the simulated environment?
Using the framing, the scene, and Coppelia scene. In the real mobile robot, don't use an encoder. Just the sonars, connection, just sonars and connect. But the mobile robot is just for using encoder and other sensors. I started the project for real robot.
You said that you use this platform, this digital twin system for learning. Do you have any application, to learning what? Robotics, to learning programming? What's your main objective?
Learning in all engineering fields, electronics, in graduation students for electronics, mechanical, and programming. Yeah, all the fields.
So that you consider do you intend to students or the person to learn to change the system to programming new robots? How do you intend that?
I intended this tool, using for mechanical, using for developing CAD, for assembling the robot, and encourage the students for electronics projects. Don't use it just the commercial boards for develop the robot, or using commercial robots for learning or teaching mobile robots.
Okay, great, Carlos. More questions? Anyone? Okay, no more questions. According to the schedule, this is the last paper of this section, the first session. I'd like to thank you very much for the presenters to be here for answering the questions and to explain the works. and to the audience, for everyone who is attending the LARS. As I told, the first session, we have a lot of good papers to see till the end of this symposium. Thank you very much and enjoy it very much. I will just confirm the opening conference ceremony. It's soon, but at 10, around 10:30.
Yeah, it will be starting at 10.
Okay.
Okay.
So in a few minutes. Okay.
Yes, in a few minutes. We have time for a coffee. A virtual coffee, no, a real one.
Yes, but we are closer to real coffees.
Yeah.
Okay. Thank you very much, everyone. See you soon.
Okay, we thank you. We ask the presenters to make an effort to answer everything in English, because we have international participants from now. So I think if you make an effort to answer the question, at least the questions in English, it will be nice, right? Of course, we understand that sometimes this is not possible if you have nothing of English, but if we can do that, let's try it, okay? Thank you. We will see you in a few minutes. Bruno, do you want to say something about the schedule and so on?
Hi, everyone. Hi. Good morning, everyone. Okay, so a few words about today's schedule. So next we're going to have the opening ceremony of the event. Then we have the keynote speaker giving his talk, Professor Wolfram Burger. And then late after lunch, we have 3 more technical sessions, aerial and aquatic vehicles, control and robotic systems, visual sensing, vision sensing and mapping. So we all hope that you stay with us for the rest of the day. Enjoy.
Okay, and just to say that we are also on YouTube. So if you wish for your students and colleagues to participate on YouTube, it will be very nice. Can you post in the chat this, Bruno, please, our site? Well, it's the NatalNet channel at YouTube. If you go there, you can find easy. Thank you. See you in a few minutes.
Can you hear me?
Yes, Carla, we can hear you.
Can we begin?
Sure, Carla. Good morning. How are you doing? Let's go ahead. You are muted, Carla. Oh, okay.
Okay, now it's okay. Good morning, everyone. I'm Professor Carla Fernandes from the Federal University of Rio Grande do Norte, and I'm here to begin the opening ceremony of the events LARS, SBR, WRE, WTDR, CTDR 2021. This year, our conference will be remote and is being organized by a team of professors from the Federal University of Rio Grande do Norte, the Federal University of Parana, the Federal University of Paraíba, the Federal Technological University of Paraná, and FEI University Center. I hope I didn't forget anyone. LARS and SBR, the Latin American Robotics Symposium and Brazilian Robotics Symposium, aim at promoting a comprehensive scientific meeting in the area of intelligent robotics, bringing together researchers, undergraduate and graduate students of computer science, electrical engineering, mechatronics engineering, computer engineering, and related fields. The events will be held virtually through technical sessions on the web, including oral or video presentations of full papers and webinars, featuring technical lectures of recognized importance in the area. LARS, SBR, WRE, WTDR, and CTDR are associated events, which bring scientific contributions to the larger event they are part of, which we call Robotica 2021. This event also includes the LARC, Latin America Robotics Competition, CBR, Brazilian Robotics Competition, OBR, Brazilian Robotics Olympics, and MNR, National Robotics Fair. We are holding the conference again in a virtual way due to the COVID-19 pandemic, but we hope to be able to hold the event in a presential format next year, hopefully. LARS starts today, October 11th, and runs until the 14th. The WRE and WTDR, CTDR will take place on October 13th and 14th. And the competitions start this week as well and runs until Friday the 15th. We hope everyone enjoys the event and can watch the paper presentations, keynote speeches, and workshop. The event is also being transmitted through YouTube, so share it with everyone. We hope everyone can watch it and contribute with us with questions, etc. First, I would like to show you a video introducing our university, the Federal University of Rio Grande do Norte. Just a second. Let me just... Wow. It's playing, right?
Just the sound is a little low.
Founded on June 2015, it has a built area of approximately 300,000 square meters, which encompasses the 7 campuses spread all over the state.
Carla, it's not okay.
Sorry, what?
It's not okay. At least here. I don't know if Bruno.
Sounds a bit low. You can just turn it louder a bit.
Oh, okay.
It's on more than 43,000 students, divided into approximately 120 undergraduate programs, 90 specialization programs, 70 master's degree programs, and 40 doctoral programs. It has more than 2,300 professors, of which more than 1,800 have a doctoral degree. It has more than 1,500 research projects and 300 community service projects, in addition to around 5,500 technical administrative staff. Among the areas of UFRN that stand out, we may mention the Brain Institute, which conducts research in the area of neuroengineering for the treatment of vascular diseases, epilepsy, and other neural disorders. The International Institute of Physics, which promotes the exchange of scientific knowledge with the international community in strategic areas. The Center of Petroleum and Renewable Energies, through a partnership with Petrobras, considered one of the largest research poles in the field, providing information for more than 1,000 professionals at undergraduate as well as postgraduate level. The National Institute for Space Research, which develops competencies in science, technology, and innovation through satellites and space technologies for the study of the climate, the weather, and the global environmental changes. The Institute of Tropical Medicine, whose goal is the study of infectious diseases more prevalent in tropical continents such as South America, Africa, and Asia. The Digital Metropolis Institute, which operates in the technical and academic formation through the social and digital inclusion of young people, from the basic education up to the postgraduate studies. The Superintendence of Informatics, responsible for the integrated system of academic activity management, an information technology system which is a reference among the Brazilian universities and also used by the Federal Police of Brazil. The UFRN Music School, which objectives are educate, produce, disseminate knowledge, and make music in order to contribute to human development, promote social justice, democracy, and citizenship. Our school hosts more than 20 musical groups and the UFRN Symphony Orchestra, one of the only university orchestras in the country. The CAENI, a permanent commission constituted by a multidisciplinary group of professionals responsible for the support, the orientation, and the follow-up of the institutional policies of inclusion for students with educational special needs, ensuring equity and accessibility for their full development in all academic actions. The NUPLAN, UFRN's Food and Drug Research Center, which is an official laboratory enabled to produce medicaments for the Brazilian public system health. Among its activities, the NUPLAN also offers academic support to undergraduate and graduate courses, promoting teaching, research, social projects, and technological innovation. The Agora, Institute of Modern Foreign Languages, Literatures, and Cultures, which has as its main objective to offer foreign language courses to UFRN's students, academic and technical staff, as well as proficiency exams in order to make their mobility abroad possible. The Agora Institute can also receive all foreign students and researchers from UFRN's partner institutions in its Portuguese for Foreigners course, free of charge. The external representation of UFRN is a duty of the International and Interinstitutional Relations Office in the area of cooperation and student and professor exchange, as well as of the Distance Learning Office in the academic area, through the provision of non-face-to-face and wide-reaching programs. Among the services provided by UFRN to its academic community are 3 university hospitals, 22 libraries, 3 museums, a digital TV channel, a radio station, a communications agency, a publishing house, a center of art and culture, a childhood education center, a dormitory, and a university restaurant. In the area of sports, the university provides official soccer and training fields, gymnasiums, Olympic and semi-Olympic swimming pools. Therefore, UFRN searches for the excellence and the academic innovation through the formation of qualified professionals and educational actions committed to the production of knowledge articulated with the social and community integration, developing solutions to the regional, national, and international problems.
I would now like to invite Professor Josemar Rodrigues de Souza to speak on behalf of the Robotics Special Committee of the Brazilian Computer Society. Is Josemar there?
Okay.
Okay.
Good morning to everyone. On behalf of the Sociedade Brasileira de Computação, more especially the Comitê Especial de Robótica, I thank in the name of the Robotics 2021 General Chair, Professor Luiz Marco Garcia, and Professor Sarah Thomas, to everyone involved in the organization of LARS SBR 2021. The Special Committee on Robotics of the Brazilian Computer Society aims to promote robotics in its electrical, mechanical, and computational dimension through scientific, technical, and educational activity, as well as promoting integration between the different actors and stakeholders in the area. CER is directly responsible for the coordination and realization of the Brazilian Robotics Symposium, Latin American Robotics Symposium, Robot Test and Dissertation Workshop, and Robotics Test and Dissertation Competition, which take place with robotics. The CER is managed by a steering committee and a coordinator who are chosen by common through election. This period, I am the coordinator, and the steering committee is composed by Professor Douglas Guimarães, Professor Paulo Droz, Professor Sarah Thomas, Professor Eduardo Totti, Professor Rosalia Aparecida, Professor Tiago Pereira. Well, I take this opportunity to remind that the Special Committee on Robotics Assembly will be held on Thursday, 7 p.m. Thank you very much and enjoy the event.
Thank you, Professor Josemar. I would now like to invite Professor Bruno Silva from the Federal University of Rio Grande do Norte, Chair of the LARS, Latin American Robotics Symposium.
Thank you, Carla, for your invitation. I'd like to thank you all. Good morning, everyone. In the name of the program committee, I would like to welcome everyone to LARS 2021. In this edition of LARS, we're going to have a total of 16 technical sessions on assistive robotics and human robotics interaction, aerial and aquatic vehicles, control and robotic systems, vision, sensing and mapping, robot soccer, and navigation and path planning. A total of almost 60 technical works were selected for being presented at LARS. I'd like to thank everyone that is helping us with this year's event, including but not limited to our reviewers, the chairs of the technical sessions, the organizing committee, and the support team. Thank you all. I hope you enjoy this year's event. Thank you.
Thank you, Bruno. I invite now Professor Juan Fabre from the Federal Technological University of Parana, Chair of the WRE, Workshop of Robotics in Education.
Good morning, everyone. Do you hear me?
Yeah.
Okay, I'd like to thank Carla, that is our co-chair from WRE 2021. That's the 12th Workshop of Robotics in Education that will be held from 13 to 14. It's Wednesday and Thursday this week. We will have technical presentations during the mornings, starting 9:30. And we will also have two invited talks. One on Wednesday, 10:30 to 12 p.m. It's Parana Robotics program, teaching robotics to students in public schools, that will be presented by Professor Marcelo Gasparin of the Secretary of Education of Parana. And on Thursday, we will have invited a talk about space robotics, the use of pedagogical platform for teaching educational robotics, presented by Professor José Carneiro from Faculty of Economics, Administration, Accounting, and Public Policy Management, and also with help from Brazilian Space Agency. And on the afternoon, on Thursday, we will have an open course, short course from 2 p.m. to 5:30 about educational robotics with open technology, Arduino and ESP32. So I invite you all that are interested in look for the link for the YouTube channel in the NatalNet area and watch our very interesting discussion and presentations about educational robotics in Brazil. Thank you, Carla.
Thank you, Professor João Fabre. And now I would like to invite Professor Júlio Melo from the Federal University of Rio Grande do Norte, Chair of the WTDR Workshop on Dissertations and Theses in Robotics and CTDR Graduate Work Contest in Robotics.
Hello, everyone. Hello, Professor. Thank you, Professor Carla. Morning, and it's a pleasure to be here. I'm on behalf of all the professors that were working on the previous versions of the previous editions of the contest and the workshop in robotics. And this year it was a very good year for master thesis, at least. We had 7 theses submitted to the contest. All of them are being presented in the main event of LARS. This year also we were able to make in a way that LARS does not compete with the CTDR. So the participants of LARS can watch the presentation of the thesis or dissertations, and it's very interesting because we are talking about the best work that at least the work that was submitted here, one of the best works in robotics that we have in the whole country, or maybe even in the South America. And we have very interesting presentations on Thursday and Wednesday. You are all invited. And last year we had very strong competitions across the dissertations, and this year especially we had two PhD works less than last year, just 2 PhD works, but I think it will be enough to satisfy the most viewers, because the works are very nice. And for master thesis, we had 7 submissions, and one of the theses were submitted straight to the workshop, meaning that they don't have the complete work. They still don't have the complete work, but they already had some results, and they were selected to present on the workshop. And so, okay, I will invite everyone. I invite everyone to go to the workshop and the contest. I think it will be very interesting. We can't. It's very hard to separate in a thematic fashion like the conference, but still works are very interesting to see and to go where are the best works are. It's a very place to be on the event. So thank you very much. Thank you, everyone. I hope to see you on the CTDR. If not, I'll be here and we can talk during the event as a host or co-host like Bruno and everyone. Thank you.
Thank you, Professor Júlio. Finally, I invite Professor Luis Marcos Gonçalves, Professor at the Federal University of Rio Grande do Norte and Organization Chair of LARS, SBR, WRE, CTDR, WTDR.
Let me see if I can present. Is it okay, Carla?
Yes, we can see.
Fine.
Okay, I made this short presentation, but the whole thing here is to thank not only our team, NatalNet, who I believe has done a very good job, but also to thank everyone who is in here now and who will be watching our event, and to welcome beside anything I say that. So I'm gonna tell here like some history, but differently from what has been traditionally done. So don't mind if you don't like it, and if you like it, you can send me comments later, okay? I think you can see here the little bags in this tree. This is, by the way, a Cattleya, is one plant from Rio Grande do Norte. It's native from here. And these little bags are meaning that we have the seed there in 2019, when at the Rio Grande City in the south of Brazil, we accepted, and also it was chosen by the robotics committee of the Brazilian Computer Society and by the Robotics Brazil for us to organize the event here last year. So then it came 2020, right? It's a little big. The pandemic almost made us to abort, but fortunately we had some water into this plant, and it's something like this today. Actually, I went there in the plant, and then this is a further picture that we took from them. Though I think LARS in 2020 and 2021, we made it. We, as I say, is not our team, is the Brazilian community on robotics. So as a researcher for a long time in this field, more than 20 years, I think I have to thank everyone from the community who has collaborated for today. We get, I mean, the second year, even with the pandemic, everything done here. Further, I have to thank very much everyone who has collaborated straight in the organization. Okay, and so I will just talk a bit about Natal. Natal is a surprising place. I think most of you don't know, even people from Natal, this place. It's closer to the, we call here, the Love Lagoon, Lagoa do Amor. Some 70, 80 kilometers from here, the place where I am now. And there are several beautiful places, this one in Natal. So unfortunately, you could not be present here to enjoy displayed. And there I can find now this Catlegra was that is the native from RN. There are several of them in there. So I think if you come and visit, most of you will enjoy it. Actually, this was the last Saturday that I came back to there to take these pictures and take some collection. So it was a challenge to make the event the first time completely virtual. I think everyone who is in the organization knows we have to work a double, and it is a double challenge to organize twice. But fortunately, the NatalNet members faced it and surpassed that. So I have firstly to thank all of you. I will not tell the names here, but everyone who is participating in our team has collaborated, and also from the university who are helping us this year, who Carla has talked about in the beginning of the opening ceremony. Okay, so many thanks to all of you. And I should also thank CNPq that just some days ago, I got the partial answer from CNPq that we were contemplated with a grant. It's not that much, but I think this can help us on the budget. Also, we have something from WebRN. SBC is our sponsor, and also IEEE joint chapter. Actually, we have here in Northeast Brazil, in Computer Science and Robotics Autonomous Society joint chapter, who I am the chair at this time, and we are going to have elections for it in a few days also. So I think this is good to have all of these organizations behind the LARS, and hopefully in next year people can get also from CNPq. By the way, we have made a correction in the number of realization of LARS. It was wrong because we didn't count until last year the first 4 editions that happened. At that time, we have the name Robotics meeting yet, okay? And then we corrected that, and I think that was thanks to this. We are now in the 13th edition of LARS. We got this grant from CNPq, okay? So I have to thank all of these sponsors who have given us. Another thing that I want to talk is about our proceedings. Our proceedings are now almost ready to be in IEEE export. By the way, I'm going to talk to our publisher chair, and perhaps we can get them available to all of you. If we can do that at this time, still today, I will make available the link for you, for all of you to have access to the proceedings while you are at the conference. I think sometimes it's better to have the paper ready while the talk is going on. Another thing, they will be available at IEEE Explore, and I think this is a good thing that we have at LARS because of this, and also the best papers at the Journal of Intelligent and Robotic Systems that we will announce tomorrow who will be there, what are the works that we have selected. By the way, we have them already, okay? We use just the GEMS scores for doing that, and I think this is nice because it's not it's objective, it's not subjective. All of this has been always this care in the evaluation of papers has been a sensitive thing that since the beginning our committee has thought about it, and the decisions were also made based on objective scores, okay? And this is good because this gives us very good visibility outside Brazil and outside South America and Latin America, okay? So I have to thank each one that contributed, from SBC to the executive committee, from the authors to PC members and also the reviewers, and also to all participants and authors who have submitted to our event this year. As I say here, all Utricularias together make a much better conference than a single one. So we are here as a whole team. I have to say that all of the time, okay? This is the Lagoa do Amor, for you to know. It's a really beautiful place, clean water. And if you come here, you can go there. And so I thank everyone, and I welcome everyone to have a very good conference in here. Okay, thanks. Okay, Carla, thank you.
Thank you, Luis Marcos. Julio asked if those were wild orchids.
Sorry?
Julio asked if those you show were wild orchids.
Yes,
Yeah.
Those are orchids.
That much?
Wild, native from our land, from our end. Besides the Utricularia, that is a plant on this, where you have a lot of water. But the other ones were orchids. Okay.
In my house, they don't last 10 days.
Okay.
They die before that.
Okay.
Okay, thank you, Luis Marcos. With that, I declare the event LARS, SBR, WRE, WTDR, CTDR 2021 open. Hopefully, this will be our last remote edition. This year, we have a very interesting program, and I hope that everyone enjoys the event and can participate through Zoom or YouTube. Now I pass the floor to Professor Bruno Silva to present the keynote speech by Professor Wolfram Burger on probabilistic and deep learning techniques for mobile robot navigation and autonomous driving. Thank you.
Thank you again, Carla. I believe the keynote speech is scheduled for 11 a.m., right? So Professor Wolfram is not here yet. Okay.
Okay.
Well, but starting at 11 a.m., we'll have the keynote speech of Professor Wolfram Burger. And I hope to see you all here. I myself, I'm looking forward for this keynote and for all the keynote speeches that we're going to, all the keynote talks that we're going to have this year. Today we're going to have a speech by Professor Wolfram Burger. Tomorrow by Professor Rudiger Dielman. On Wednesday, we're going to have a talk by Professor Carmen Torras. And on Thursday, we're going to have a talk by Professor Flavio Tonindandel. Okay, so yes, we think I think I have a little bit of a break, as a coffee break time. It's a virtual one. In the meantime, I invite you to join our Discord servers. There are a few lounges configured there, so a few audio rooms in which you can join and talk to each other without disrupting this the main track of LARS. Okay, just a second. I will post a link here. If you use Discord, you can join the server and, well, gather a few colleagues or a few friends and talk to each other without disrupting our main event here. Okay.
Bruno, is the link available on the website?
Yes, it is.
Okay.
Bruno, can you talk a little bit about the breakout room also? I think it's good for people to.
Okay, so if anyone desires, we have a breakout rooms here on Zoom. It's a separate room from this one, in which you can join and prepare it for your talk, prepare it for your presentation, check your microphone, or check your camera, check your presentation volume, and anything like this. I think that this is the main use of these rooms, right? This is what we planned for. But well, if you want to, you can join this breakout room. You can find this breakout room right here on Zoom. You click the interface of Zoom breakout rooms, and then it's going to show salas simultaneas, and then you can join the other room, and everyone that is in the other room will hear each other, but we here in the main room of LARS, we're not going to be able to hear anyone that is there.
Also, the video there is not broadcasted to YouTube, so you can try it if you want the presentations and everything.
Just remember when you leave it there to press the green button, right? If you press the leave, you're going to have you're going
to re-enter.
To re-enter here again. If you press the green button, it comes automatically to here. It will not shoot you down from the Zoom. Bruno, is this Discord in the YouTube? Can you put that in the chat?
Okay, I think Duffrey is listening to us. I think Duffrey can insert it in YouTube.
Can do that. Please, Duffrey. Okay, so we have a little break now.
Professor Bugart, can you hear me?
Yeah, I can hear you. Thank you.
Yeah, we can move to the breakout room and test your presentation there if you want.
Yeah, let's do this.
Okay, I'll go there. So we are a bit ahead of time. We can, if Professor Bogart wants to start right now, we can just start a bit early, just a few minutes. I think it's okay, if it's okay for him. You are muted, Professor. Okay.
For me, it's fine.
So could you please, the host, could you please stop sharing so Professor Bogart can start?
Okay.
I will just present him to everyone. So we are going to start right now Professor Bogart presentations. Professor Bogart is a professor from Uni Freiburg in Germany. He is the head of the lab for autonomous intelligent system. He studied computer science at University of Dortmund and he has his PhD on Unibon, also all of them in Germany. His presentation is about deep learning techniques for mobile robots, navigation, and autonomous driving. And he will be presenting from this time to close to 11 a.m. I'm talking Brazilian time, Professor Bogart, so you have to convert the time schedule. And it's a pleasure to be hosting a fellow German presentation. I was a student in Uni Bochum for a kind of for my PhD thesis. It was very nice to be there, and I also know Dortmund and Bonn. I really like the area, the Ruhr area. It's very nice, very warming. So thanks, Professor. Presentation is yours. You can start when you want.
Okay, Julio, thank you. Thank you for the invitation, and also to Eduardo for inviting me as well, and reminding me of that meeting and sending me nice pictures from the venue, which I really enjoyed seeing. I would have loved to be there in person, but unfortunately, time is not yet ripe for this. So today I'm going to talk a bit about probabilistic and deep learning methods for robot navigation and also autonomous driving. And it is a little bit of a maybe tutorial of that what we did in probabilistic robotics, and that where it brought us to, and then also talk a little bit about the limitations, about like the gaps that we actually need to fill to build truly autonomous robots or self-driving cars, which will bring us then to deep learning techniques. And then in the end, I will speak about that, the relationship of the two, and I hope that it will also stimulate a discussion about this. In general, like we all are interested in building autonomous robots, basically systems that act autonomously and by themselves in their environment, perceive the environment, and generate actions to achieve their goals. And when you think about this in terms of navigation, then this is basically like using the sensors to decide what to do next and where to go next. And in many cases, these systems then actually build a map that is a representation of the environment that allows, for example, path planning and many other functions. We'll talk about this a little bit later as well. So that, and these maps are then used for example, path planning. And in order to do path planning, then what is needed is also a proper estimate about where you are, because then you are able to basically plan a path from your current location to the goal location that you want to reach. So these are the key functions that we need, basically being able to map the environment and being able to localize in a map generated from the sensor data. And then in navigation, turns out that what you actually need to achieve is being precise in terms of localization, so that the vehicle actually knows accurately where it is relative to the given map. You also need to be able to do robust mapping in the sense that we can build maps effectively, and then also do this in a term of long-term autonomy setting. And there you see already that long-term autonomy probably means that we are able to actually need to be capable of rebuilding maps on the fly. And the applications of this are manifold. These are robots in logistics, transportation systems, assistant robots, and also self-driving cars. This is where we all need this highly accurate navigation. The problem is there's no such thing as a perfect sensor. So basically every sensor, and this is an odometry sensor, this is the path that the robot took. And if you take the odometry, then so the wheel turns basically and do a little bit of geometry, then and to recalculate the path the robot took, then you end up with a trajectory that is by far not consistent with that what the vehicle actually executed. And same as with range data, some of these, and this is an ultrasound measurement, correspond to that what you would expect. Black is obstacles, white is free space, but in many cases they are actually not corresponding, and particularly when you go into a highly dynamic environment. And this is a LiDAR range scan, so a sensor that provides you typically with highly accurate estimates about the distance to obstacles, which are depicted in black here. But you see the majority of these measurements actually ending in free space, which is white, which means that they are corrupted. And the reason is that the robot is surrounded in this case by people obstructing the LiDAR sensor measurements, and in this way leading to false interpretations. Despite of the fact these systems need to be able to actually robustly operate in their environment and accurately navigate around. And the key weapon that for this purpose is basically probabilistic robotics, which is an explicit representation and utilization of uncertainty. And for those of you who don't know what that basically means is, in the end, we are interested in estimating a probabilistic belief about the state X of the system, given its measurements Z and the controls U. In case of navigation, this is just the distance measurements, can also be camera images, and U is the movements that the system executed, and X is the state. And if you have a robot that lives in a plane, so it would be X, Y, and the orientation. And then that what you see on the right-hand side is a base filter that incorporates new movements, basically by integrating over the existing belief and multiplying that with a probability that this control led the system from X prime to X. And then when you get a new measurement, then you multiply the resulting belief with the likelihood of that measurement given the corresponding pose. And the normalizer here basically takes care of the fact that the belief sums up to 1 after that operation. And in utility optimization, this is a specific form from reinforcement learning or Markov decision processes. You're basically interested in calculating the utility, the action that generates a U, so finding the U that provides you with the highest future reward, or that maximizes your utility. So the key questions in this context is like how to basically represent the belief over the state, and maybe even to maximize it, and in particular in the context of higher dimensions. And in robotics, we found a couple of ways to represent the objects of interest. So for example, representing maps, there are different ways of doing this. This can either be so-called occupancy grid maps or landmark-based representation. People also use just point clouds or even meshes. And these are different types of representation of the environment. And for the belief that people use, for example, the Kalman filter, which are Gaussians, strictly speaking, particle filters, and then again, discrete representations, and also optimization methods, in this case, a smoothing type of representation. So, and here is like a visualization of what that actually means, probabilistic localization. So we are basically representing a probabilistic belief over the state. In this case, it's a one-dimensional space for this robot here living in this corridor, which is able to detect doors. And what this robot basically does is whenever it detects a door, it multiplies its current belief with the observation likelihood over here, uniform times the Gaussian, the observation likelihood gives you that function over here. And whenever it moves, it applies the right-hand side of this equation. So it integrates over that belief that we see here and multiplies it with the likelihood of ending up in X, given you execute U in X prime. And that basically, in this case, corresponds to more or less shifting this belief and convolving or smoothing it. And yeah, once again, when the robot measures the door again, then you basically end up multiplying it with the likelihood function again, which is this function times this function gives you this function. And now the key question is how to effectively represent this function. And for many, there's no general closed form representation, so that we actually need to deal with approximations of these of the true belief of the system. And one particular interesting approach in this case is a so-called particle filter, which is nothing else but a set of hypotheses or weighted hypotheses that represent the individual or potential states. And it's a finite set that represents basically, it's a set of potential states the vehicle might be at. And here you see one application of this. It's particle filter with 10,000 hypotheses that actually try to estimate or represent the belief of that system. And you can basically, in a global localization context, where the robot tries to figure out where it actually is, starting from a uniform distribution, where the robot is not told where it is in the very beginning. And you can see how these peaks evolve, which correspond to the ambiguity in this corridor. And in the end, by entering this room, the robot actually figures out where it is. And this is a very, very popular approach for localization, which has the particular advantage that it is, due to the ability to deal with nonlinearities, very, very robust, and at the same time also allows global localization, basically localization from scratch, and also dealing with that so-called kidnapped robot problem, where whenever the robot made a mistake and got a wrong estimate about where it might be, you can actually easily recover from this. And the key question, however, for industrial applications is how accurate can you actually get? And here is an application of this with a slight extension in the end, with a representation that allows the robot to do fine adjustments. And the black stripe that you see here on the floor is only for visualization purposes, so that you can see how accurate the robot actually is in reaching the desired target location. And it turns out that this robot that we used over here, in this case, the controller on the robot was actually not accurate enough to execute the motion commands, so that we basically distinguish between the localization accuracy, so how accurately the system knew where it was, versus the positioning accuracy, where the vehicle actually is. And it turns out that the localization accuracy was higher than the capabilities of the platform to localize itself. You can also extend this to larger platforms, and this is a 11-ton vehicle loaded with 2 big blocks of concrete, based on safety scanners that you see basically between the second and the third wheel. And again, like what we did there is we basically also introduced additional obstacles to actually obstruct more and more of these LiDAR beams, and try to figure out how much error by how much we increase the error in the localization. And what you can see is that the translational error is in the area of millimeters here, and that actually increases when we go to dynamic environments, but only by a very, very small margin. And even the maxima are very, very limited, like within the range of millimeters here in this case. And same for orientation, we do achieve highly accurate orientation estimates. So this is like a robust approach that actually allowed us to introduce this into industrial processes, and that was actually a collaboration with KUKA, where we basically developed such platforms, or the software for such platforms, that can be used in transportation tasks for the 777 fuselage, and for bolting processes for fuselages in general. And so with this, you can actually get very, very close to industrial processes. And you can also do this. You cannot only do like localization then with LiDARs, right? If you think about cheap cameras, then you can actually utilize the very, very similar approach for monocular camera estimation in 3D point clouds, like generated by LiDAR scans, for example. And here is an approach where you basically used the monocular tracking approach, I think in this case from Slam, and performed scan matching with these with the point clouds stored in advance, so that we could actually localize the moving camera, and this is a Kitty data set in this 3D mesh. And you can even go to very, very cheap cameras. So this is a Freiburg data set where you basically can use your smartphone camera. This is at the beginning a data set with Canon S100, but we in a second actually switch to an iPhone camera. And what we do on the left-hand side, what you see also is we basically project the color of the pixels onto the point cloud just to visualize how accurate we are. And the trees are in light blue simply because the branches are not there where they were in the mesh. Right? So, and if you delocalize a branch slightly, then basically pick up a light or a sky pixel from, and this is why the trees look light blue and not blackish. So that all required the ability to basically have a map, and we will talk about this as being a limiting factor in a few moments. But first, let's talk about how to actually acquire maps, which has been for a long time seen as a chicken and egg problem, because what we have seen before is we can localize in a map. It is also has been known that we can build a map once we know where the vehicle is, but doing this at the same time was actually long regarded as a chicken and egg problem, until people found out that you can actually estimate both at the same time. And just to give you an intuition why SLAM is complicated, again, this is a trajectory of a robot with LiDAR measurements projected into the space, given where the odometry basically tells where the robot is. And then what you end up getting is a map like this, which is pretty useless for navigation. So in the very beginning, the question was, like, is there a way to calculate a map that we can then use for localization purposes and get these robust navigation systems for more or less static environments? And again, the interesting aspect is that the very same equation that we saw before can be used for that purpose as well. If you allow the fact that now all of a sudden we go from 3 dimensions, which we did in localization, to in the order of 10,000 dimensions, which is hard to be dealt with within a particle filter. Although actually there was a discovery by the end of the last century that once you sample the trajectory, you can take the trajectory for granted, and that separates the graph and substantially reduces the complexity of the mapping process. And that's basically a factorization that you see here on that slide, where you basically have a particle filter representing trajectory hypotheses, and then you can basically perform mapping with known poses. And then you end up doing the very same that we saw before. You have now trajectory hypotheses instead of pose hypotheses. And then for every of these trajectories, you can directly associate a map. And the very same process that you saw before on the particle filter can now be used in an efficient way to build maps. And this is the very same data set that we saw before, where now the odometry is basically corrected, and we end up getting a proper and accurate map that the system can use for navigation. And so the alternative to this is going to a smoothing solution, or graph-based SLAM, treating the entire system as an optimizer, or the entire problem as an optimization problem, where you're basically interested in minimizing the error. And that is the error between observations of already seen aspects in the world relative to the measurements that you obtained most recently. And this is basically what you're interested in, finding the poses that minimizes this squared error down here. And the idea here is basically to formulate this as a graph, or consider this as a graph, where you basically take the trajectory of the vehicle, and it's mostly seen down here, the trajectory, and that is nothing else. So odometry basically provides you with so-called constraints between consecutive poses. When you move from A to B, the odometry tells you what the relative displacements of these poses is. And then you can also have observation constraints. So for example, this area over here looks very, very similar to that area over here. And what we then do is we basically introduce a constraint over here that tell us that this pose actually needs to be over there. So in such a observation constraint is nothing else but also a relative transformation that tells us where we need to move that point in order to match it, to match the observation. And so what we now do is we construct this graph and you can consider this as a mass spring system. And these masses are the individual points where the robot actually received observations, and the springs are like connecting those masses in a way that they actually are completely relaxed only and only when those points exactly match, which means or correspond to the relative pose actually estimated, which means that this spring here must be very, very elongated and introduce a large force. And in other areas where you only have, for example, odometry constraints, like over here, you also do have potentially smaller forces. And what the system now does is it throws these mass spring system into a bath of oil and let it relax until it reaches a global or local minimum, ideally the global minimum. And once we have done this, we can basically re-render the map. And underlying this is nothing else but the least squares optimization approach. And with this, you can basically build highly accurate maps. And this is kind of still the standard way of generating maps. Although over the past years, there were more and more effective solutions to this optimization problem. And so here you can see, for example, an online correction of maps. You can also use this in a batch fashion, or you can even go very, very wild when you initialize everything with 0, 0 and a random angle, hoping that the SLAM system will then unfold the map in the correct fashion. So this is basically how mapping works or SLAM works. And the interplay between SLAM and localization now is that we build a map in advance and then later on keep the map fixed and only perform localization. You can also do this in 3D, by the way. This is a simulated sphere data set. And what the system now has to do is recover the original poses of the sphere that we randomly distorted. And from the shape here, you can see that the approach actually nicely converged. You can also then apply this for larger outdoor structures. This is a mesh representation of a large parking garage that you then can use like with LiDAR range scans, for example, for positioning your vehicle. But you could also imagine now using just the monocular camera in this vehicle to localize it and to use it, for example, for valet parking purposes. So if you want to have like a cheap self-driving car that can perform self-driving in parking garage, then such an approach could actually work out. So it would be some sort of a cheap valet parking application. So that is basically the idea of having of how this all is done. And these maps have been shown to be super useful, and there are different representations actually that are used, for example, in automated driving and robotics. And on the top, you see, for example, a high definition map that is used for automated driving vehicles, where you basically see like line features and point features like poles and corners that the vehicle then uses for accurate localization. There are other applications as well. So if you look at this map down here, then this is, I don't know exactly what it is, but it looks like a ground map that Waymo published once on its website. And I guess that what they are doing is they're basically removing this ground map from the current scan, and in this way have an easy means for getting or cheap means for getting like isolated objects out of it, like basically cars, everything that stands out of out of the ground will then basically be directly be separated. But there's other aspects that are needed. For example, here this is an intersection map, and this is basically one of the key problems in automated driving, that you need to have like the connections of lanes in intersections. You need to have data associations between traffic lights and lanes in order to actually allow the vehicle to exactly know as to whether it is safe to go or not when the traffic light shows green. So these maps are extremely useful, but at the same time also extremely expensive to maintain. And particularly when you think about dynamic environments, changes, and information that go beyond geometry. Right? If you look at this over here, this is mostly geometry on the right-hand side, right? But on the left-hand side, there's also semantics. This is data association, which basically tells you where the individual traffic lights are. And interestingly, we can more or less robustly, we are not perfect, do this. Humans can do this. But doing this with a vehicle automatically is actually still an open question. And so the key problem is, how do we get the semantics? How can we react to changes? And can we potentially infer maps on the fly? And we will discuss the third point at the very end a little bit as well. So yeah, in the top, like you see what can go wrong. So if you imagine that you do have a vehicle and you use an HD map with like line features representing the lane markings and poles, and you have an environment like this over here, then like challenging weather conditions, then you immediately see that that might potentially go wrong, and that the vehicle actually doesn't know anymore where it is supposed to be. There can be even more simplistic changes to the world. If you look at the bottom, this is actually a screenshot from a video from a guy called JJ Ricks that takes the Waymo self-driving car into challenging situations. And you can see here a situation where it actually got stuck in Phoenix somewhere. And simply what you see basically is on the bottom right is the online screen depicting the fact here that there are basically 3 cones in the lane of in the road. And the vehicle actually doesn't know what to do with these 3 cones. And so this is a very, very subtle and minor change, but the vehicle in this case is unable to actually deal with this. And so which indicates that we need to have the ability to basically react to changes, detect them, and then also properly react to them. And they are extremely expensive. Maps are extremely expensive to update. And on top of this, this is basically the barrier to level 5, the inability to deal with arbitrary situations. You can easily imagine that if your mapping or SLAM system is able to deal with arbitrary situations, right, then we would have reached level 5 to some extent. So what I'm going to talk about is a few challenges or few approaches that you actually need to get towards this and get towards more autonomy in self-driving cars. And the first one is that like change detection, and this is what many of the OEMs basically do, is performing crowdsourcing and to utilize like the situation that we have mixed self-driving and human-driven vehicles, and basically utilize the sensors in the automated driving assistance systems or advanced driver assistance systems for detecting changes and building HD maps. And then I will talk about other aspects, like including how to get semantics, how to perform tracking, which is also a complicated issue in automated driving, and also how to get the topology. So inferring, for example, these intersections, that is a long-term goal, but even for like this individual observation, trying to figure out where the individual lane markings, or what the individual lanes are and in which directions they go. So this is work that has been done with one of my PhD students, David Punn, and people from BMW a few years ago. And the idea there is to basically like perform lane change detection given HD maps. And I mean, what we wanted to get rid of is the need for like repeatedly going with these super expensive sensor vehicles through the environment in order to figure out as to whether something has changed. Instead of what we're interested in is this question, like, is there a way to utilize the sensor setup that we do have in modern ADAS systems, advanced driver assistance systems, to basically detect changes in the environment? And motivated as this by this heat map that you see over here, is basically the coverage of, in this case, all BMW vehicles in one day. as far as that could be recorded from the ADAS systems. And from this, you can see that actually it should be doable to perform a substantial amount of change detection and utilize these vehicles for detecting changes in the world that maybe need to require a remapping then. And the other question is, what type of sensors do we have available in order to actually perform this? And there's like in these ADAS systems, you typically get something like the vehicle position, odometry measurements, GPS, lane marking observations, and road edge observations. And in the HD map itself, even in modern cars, you might have lane markings and road edges in order to actually tell for example, in the navigation system where the vehicle is and so on. So, and the question is, like, can we utilize such information in order to detect changes, and how to do this? And here is an example where you can basically see how the vehicle, like this test vehicle that we are using for collecting data, tracks the individual features in the environment. And now the question is there a way to figure out as to whether the environment has changed? And based on this information on its own. So what we do is basically in this case, we used again a particle filter to detect the innovation. You can, in the particle filter, look at the likelihood of the observation likelihood to actually basically identify or detect the innovation that you have in the environment. And what we used there in this context is, as I mentioned already, the odometry, the GNS system, lane markings, road edges. But in order to make this more robust, we actually used an AdaBoost approach for the classification purposes. Still, this was not robust enough in order to basically utilize the fleet information. We wanted to be performed, or we created bins along the road and collected in every bin the individual votes of the AdaBoosts running along that road. And depending on like how many reds and greens you had, you basically voted for a change or for no change or a change decision in this particular bin. And so this is basically the idea here. And here you can see like visualizations of these of this in construction settings, like over here. What is interesting is so like the system believes more or less that up to here there's no construction zone, and then as soon as the road actually goes over to, or the new lane goes over to the right of the original lane, then it identifies that there's a change. What it doesn't detect here, and this is why, simply because we didn't use color information, that the construction zone starts over here already, where you basically have the yellow lanes, but we didn't incorporate this, and this would be an extension of this in order to actually make it more robust to just lane marking changes in the system. So this is one of the results, and here you can also see how much it improves when you go from a single trace classification to a multi-trace classification. So it basically shows that like multiple observations and this crowdsourcing idea actually improves your classification result. So that would be a potential solution for the fact that we are still like using maps, but then want to detect as to whether it has changed, and maybe go there again with one of these expensive sensor vehicles to actually create a new map and give it to the map operations teams, and then create a more accurate map, upload it to the self-driving cars, so that we can basically still live in this regime, like we use a map for localization, which the majority of vehicles nowadays do. The key question is, like, and that's what I wanted to discuss also, is there a way to basically get rid of this or relax this assumption that we always have an accurate map? We have seen that we still can perform accurate localization, but in a traffic setting for vehicles, when the map changes, then the vehicles also need to go somewhere else. So there is a need for basically remapping. And there's a way to get rid of this, but that would require to be able to basically estimate semantics, performing data associations, like be able to perform tracking, and also infer the road structure and the intersection topology. And this is an enormous challenge. And I would just want to talk briefly about a few ideas how to do this and things that we worked on in order to make vehicles more autonomous in particular with the view on challenging and changing situations. And one of the works that we did over the past is like these LiDAR panoptic segmentation, basically taking images and trying to figure out what is what in the environment. So what you're basically interested in is knowing what is cars, finding traffic lights, vegetation, sidewalks, and so on and so forth. And once you have that, then you can potentially start looking into approaches where you are not like leaning on a map and where you can basically navigate without an HD map. And but that basically means that you take your vehicle and take all the 3D scans, like in case of a LiDAR, and then perform an interpretation of what this is, like what does the environment look like, and what can I do? And so there are different tasks that you would need to do. For example, starting with a LiDAR scan, as you can see here on the left, you want to do, like in the first place, do something like semantic segmentation, like figure out what road is, what walls are, what trees are, what cars are, and then continue from there. But you don't want to only have a car class so that color every car pixel or car data point blue. You actually also want to do instances, because that will allow you to make better prediction about how the world is going to evolve over time, right? So it's not going to be the case that all of these vehicles are going to move, but potentially one of each is going to move in a certain direction, and depending on where this is, you can make better predictions. And so that basically means that we need to have some sort of instance segmentation, which is then, if you combine those two, then we end up having that what is called panoptic segmentation. And for that, we developed a deep learning approach where with an architecture that is called the efficient LPS architecture, which has a couple of innovative components. For example, here, these range encoder network, then a feature pyramid network, and proximity convolution module. So I think here is like to give you a glimpse of what this proximity convolution module does. It's basically, normally the convolution works uniformly, but in these depth image, you typically have like particularly when you look at edges of cars, then some of these pixels are basically in areas where you don't have car. And there you want to be potentially more flexible in order to convolve over the semantic classes and not just uniformly. So this is one of the aspects that components that was done in this architecture. And going back here, right, so this is basically the backbone, and then we do have a semantic head and an instance head, and they are combined in a panoptic fusion in the range image, and then we perform a back projection onto the LiDAR scan in order to get the LiDAR panoptic prediction. And yeah, you can see like the results on two evaluation data sets, semantic kitty and use scenes. So typical results of scans that we have. At that point in time, we basically made it to the #1 of the leaderboards, which was pretty good at that time. Right now, people have become way better at this, but this is how science works. You know, in order to can only advance it, and typically after a few days or weeks, and other people are better, which is great. But at that time, we made it to the #1 on these data sets. And here's a qualitative result for semantic kitty and you can see here like how these individual objects are in the data points are put into different categories. Yeah, so the key question now is how to continue from there. And the problem with panoptic segmentation is that it is just like a one-shot segmentation. That means that you only do look at every frame individually, which might lead then to, if you look at this over time, might lead into inconsistencies, temporal inconsistencies. At the same time, like there's multi-object tracking approaches that are actually able to track individual frames over time bound in boxes. And the question is, like, is there a way to combine this and to basically end up having multi-object panoptic tracking so that you have like temporal consistency, which then will allow you to make better predictions, for example, in tracking systems. And yeah, this is also our recent work on multi-object panoptic tracking, MOPT, with this team on the top here. The idea is basically depicted in this short video snippet where you basically get out of the semantic segmentation and the instance segmentation and the tracking, multi-object panoptic tracking. And you will see more like longer video in a few seconds. So this is again the architecture where we have an instance tracking head, an instance head, and a semantic head, and we combine all those three to basically in the end get the multi-object panoptic tracking. Again, two evaluation data sets, vision-based MOPT on Visual Kitty 2 and on semantic LiDAR. And again, this approach, we also made it to the #1 of the leaderboard at the time when we published this. And here you can see a typical result. It is not perfect, as you can see, like this bluish van switches to greenish, which means that there's a tracking error. But I mean, the idea is that with approaches like this, you over time get a more consistent and temporally consistent representation, which then allows you to make better predictions. So that will basically allow you to infer like where the vehicles are moving. And once you have seen how vehicles traverse through an intersection, you can also make predictions about where you should go once your traffic light turns green. Here is our results on, again, on this left-hand side for panoptic tracking as panoptic segmentation, and on the right-hand side for panoptic tracking. What you can see here is basically that the vehicles parked at the side of the road, that they have consistent colors on the right-hand side, which means that you're basically able to maintain the object IDs over time, which is not possible with the semantic segmentation approach on the left-hand side. And you can also see once the vehicle arrives at an intersection, which should happen now in a second, as far as I know. Then, this is in the next video. Let's go. Yeah, so let's go here. You now see the vehicle arriving at an intersection, and this green tornado there, and the red one is basically the tracking of objects over time. There was even a pedestrian on one side of the video. So these are approaches for basically inferring semantics and also temporal consistency. But the limitation of this again is that this mostly only works on daytime images, as most of the data sets are basically for daytime. But if you think about like autonomous vehicles, then you also want to be able to operate them at nighttime as well. And this is something that we have been looking into in the past in utilizing additional modalities. So in here on the left-hand side, you can basically see a video of a nighttime sequence. And on the right-hand side, you see a conventional CNN trained on a publicly available data set and thrown at this nighttime data. And as you can see, the semantic segmentation quality is pretty bad. And the key question is how to improve this. And that what we were looking into was basically using thermal images and or thermal cameras from which we assume that they show like a different or smaller domain gap between day and nighttime, simply because they like provide you with a figure of the heat, which is different at night than during day, but the changes are not that significant as it is with normal RGB cameras. And the idea there was to basically create a heat net that we used for RGB and thermal classification. And basically the idea was to use an RGB teacher for that is suited for RGB images and train our heat net in a way that it produces outputs that look like those generated by the RGB teacher. And so by this, we were basically able to learn how to properly classify these images. And this is basically what this network does. Here's a vehicle that we used for collecting data. This is a thermal camera over here. So 2 RGB cameras. What we are created out of this, the data is a publicly available data set, thermal CS Unify.de. You can basically download the data set and experiment with it yourself and trying to figure out how your approach potentially performs and improve on that. So it also contains a few images labeled by us. So the ground truth images. And I can tell you that labeling nighttime images is extremely painful. Labeling daytime images is already complicated, but nighttime is even worse because it's close to impossible to figure out what is what in these dark pixels. So in here you can see a few experimental results that we obtained with our HeatNet system. So you basically see that on the top you see an application to RGB images with like the teacher and the RGB net producing decent results compared to the ground truth as well. On the right hand side, in the bottom you see the application to a nighttime image where you basically see that our RGBT network performs way better than the RGB teacher and compared to the ground truth here. What is interesting is that our network also was able to, like if you remove the thermal component during runtime, then it still can produce results that look way better than that obtained from the RGB teacher. So this basically indicates that you could, in principle, use the thermal camera only for training purposes. And if you want to apply this system, then with RGB cameras only, that should also be possible. That is the interesting result here. And here's another qualitative result on a data set also collected in Fabre, where it will turn dark in a few seconds, as you can see here, with our HeatNet, like nicely picking up things like the bicyclist or parked cars and so on and so forth. So that is also an important aspect that we need to be aware of, like that we need to make these systems operate or work properly under all circumstances. And that can basically involve a substantial amount of efforts and things that we haven't worked on thus far. At the end of this presentation, and I'll be done in a few minutes, I want to briefly, very briefly talk about a very recent work that where we try to actually figure out that what I mentioned in the very beginning, to infer the lane graph, right? So what you're basically getting is some sort of an aerial image or the so-called bird's eye view representations for different modalities. And what you would like to do is infer, for example, the center lines of the individual lanes in order to know, for example, the connectivity of at intersections or the road. And like that was the key question. So can we basically learn HD map information from bird's eye view sensor data? For that, we developed a dedicated approach. On the left-hand side, different map layers for different modalities, LiDAR, semantics, and throw this onto a lane graph network and get out a directional lane graph on the right-hand side. And here you can see a few results that we obtained with our approach. So left-hand side is always the ground truth, and this is our approach. As you can see, it is not perfect, but it performs reasonably well, and so well from my perspective that I felt this is a promising approach and idea to continue with. It is also not that as perfect as I would like to have it on for intersections, which are the major challenges. So there's a lot of work to be done, and this is also something that I think will bring us closer to truly autonomously navigating vehicles that don't require maps or upfront maps to have. That brings me to the end, right? So I hope that I could convince you that the key to robust robotic and autonomous driving systems is probabilistic approaches and machine learning. The challenges there, particularly in machine learning, are the data bottleneck and reducing the labeling efforts. But at the same time, we are in the situation, or at least for me right now, that I believe that if we want to really go beyond level 4 or want to be more effective, even in terms of level 4 automation, then we need to be able to learn maps on the fly. And that brings us then in the end to the question, will we need probabilistic approaches at all? And will we need maps at all? Would be at least a very, very interesting outcome if in the end, like the learning-based approaches are so robust that the map-based approaches don't provide us with any benefits anymore. And with this, I want to stop here and to leave the floor for your questions.
Thanks, Professor Wolfen. I believe we have already a question from YouTube from Professor Rosalie Romero. She asks how the information is fused at real time. Is it possible? Does the system has a good response in terms of time? The systems you presented, do all the networks have very good real-time response?
That's something that I would actually need to ask my students right now, as whether this is the case for all of them. I don't exactly know, but in principle, I mean, right now with the because they are just like in the segmentation or in the forward direction, I would assume that they are reasonably fast. And there's still always the option to actually also reduce network complexity, and if not, then this would also be a perfect area for future work and improvements. But I can look this up if you want, and if you drop me an email, then I will look this up and let you know.
Okay. There are lots of questions in the chat. I will just go forward to them. Professor Paulo Drews, he asks if what are the main challenges to deploy these approaches to real autonomous vehicles in level 5?
Yeah, I mean, we are not there at level 5. We are even not really at level 4, maybe like close to level 4. But as you could see, that even minor changes to these environments might make your vehicle get stuck and not work anymore. And I think, I mean, this is still this heavy tail, you know, or the long tail of all these corner cases that we don't know how to solve them. And I think that we just need to go further there. And whenever we encounter problems or things that the vehicle cannot handle, then we need to work on these challenges that come up along the way to level 4, and even level 5. I mean, that would mean that we are basically, because it is nobody believes right now that we are going to be able to build maps that we build for level 4 vehicles right now for the entire world in order to achieve like this level 5 automation. So then we really need to be able to learn maps on the fly. And this is something that only like very, very few people try, and something that we haven't achieved, at least from my perspective yet.
Yeah, I think this also connects directly to Professor Eduardo Todd. He's asking, how do you see learning in semantics and building local maps on the fly? I think it's very close to the last point you just achieved.
Yeah, I mean, in the end, it is you take your observation, right, and then you want to know what is the road, what are the cars, what are the people, and how is the road connected, and where can I go? This is something that you actually would like to obtain, or the ability that you would like to obtain.
Yeah, it's a very nice point. I have also. Do we have questions from YouTube? So I can forward, Professor. I have some other questions. In the beginning, you showed a very nice approach about crowdsourcing the maps. I really believe that crowdsourcing is a very valid point, but do the crowdsourcing itself, acquiring data from people, isn't it a problem in the legal point of view? I mean, because you buy a car, but your car is selling or using your information without your knowing, and maybe if you don't want to participate, the car can't be autonomous. So it's a kind of chicken and egg another problem.
I mean, this is a very interesting question. So I think this has different dimensions. So one is definitely your willingness to share data. I mean, to a certain extent, you can do this right now with your smartphone already, and basically provide your movement or your velocity to your navigation system that you are using, so that it gets a better estimate about where traffic jams are and where not. And I mean, of course, so I think people need to have the right to say no to such things. On the other hand, in some cases, I'm a little bit more on the optimistic side there, that it should be a community effort where we all contribute to something. Like we see this in our societies right now, that this community thinking doesn't always work, right? If you look at vaccination, there's also many people who simply do not want to contribute. And I think it is important that we leave the people with this opportunity. But this is only one aspect, that I mean, in the end, it could even be that you make these solutions more attractive to people who contribute, so that basically people who contribute the data get to know where the end of traffic jams are and the others not. So that would be like, if you probably need to enforce things like that. But there's other aspects that are also very, very challenging. So, for example, imagine that someone intentionally takes its GPS device along a different route, right? And then all of a sudden, or always drives over the sidewalk, right, at night when it's empty, in order to trick the system and to convince it that the road now goes over the sidewalk. Right? And then on the next day, then all of a sudden all the cars drive over sidewalks. The system believes, right, that the map has changed. So there's many legal aspects, and we actually need to be very, very careful when we do something like this.
Bruno, I believe you have some questions.
Hi, Professor Berger. Thank you very much for accepting our invite for your talk in LARS. I think I have a more of a broad question. From your experience with the robotics industry, what can you say about job opportunities in robotics? Are these jobs still restricted to graduate or engineers or scientists? I mean, people with a PhD degree, or do you think undergraduate students also have opportunities in this industry?
Well, right now, I mean, if you can do like probabilistic robotics and even better with also have some affinity to machine learning, then you do not need to have a PhD in order to get a job. You know, that is right now, like they are like basically offering you a lot of interesting opportunities once you got into this and you out yourself as an expert in this domain.
So this is directly related with my second question, which will be what is the most important skill nowadays in the robotics industry? I mean, the one with the highest demand. I think you already answered it.
Yeah, I mean, I think in this entire space, it is like probabilistic approaches, machine learning, and a little bit of computer vision.
Thank you.
Okay, Professor Todd.
I just would like to thank Wolfram Burger for accepting the invitation for LARS. It was a great talk for us. Thank you very much.
Thank you, John. You're welcome.
Yeah, I believe we can talk a bit more. We have some we have a bit more time. If Professor Burger can just spend like. Okay, that's nice. So I have we started about the legal issues on the crowdsourcing, but still when I see presentations on autonomous cars, it's very nice to see how the segmentation and the identification of objects in the scene are going, and it seems that they are going very well. I know it's a difficult issue, so it seems last year we saw also a very impressive presentations on autonomous car from a professor from Ireland, I think, and all of them, yours and all of the other presentations, they focus on segmentation and identification of items and changes on the world, but I'm more concerned about the privacy of these data, because if you think you have an autonomous car and another person has an usual car, and you can identify which car is which, and you can just use any autonomous car to follow someone. So is there any work on nullification of data? I mean, in some way that, okay, the autonomous cars, they have the need to know where the cars are and if they are cars or not, of persons, but they can also be used to identify the specific car and the specific person. Do they work in this direction?
Yeah, I mean, that's a good point. Of course, I mean, anonymization is an important aspect. So yeah, we have been working on, for example, on data from people in hospitals to actually do like for assistance systems there. And there you also need to have the ability to basically anonymize data. And in our case, so my experience is that going from vision to depth, right, actually helps, right? So although I think that I mean, in some cases you might even be able to identify a person in range images, right? So this is something that is pretty challenging. And then, of course, right, it is a key problem. And I mean, anonymizing faces also will not solve the problem, because then, for example, the system will only be able to detect people whose faces are anonymized, you know, And so training something like that will be immediately introduce biases that are disadvantages for the system. Same with license plates. You know, when you start blurring license plates, then the system will only like maybe identify cars on your data set because it's blurred over there. You know, and you never actually know as to what that is. So this is an enormously difficult problem, and I think we don't have a proper solution to that right now. But some people are actually working on these issues as well and trying to perform learning in a more or with less biases and removing biases in learning and things like that. But it is an enormous challenge. I agree.
Yeah. We have a question in the chat. What do you think about Tesla AI, autonomous vehicles? Is it possible to rely on image data considering safety?
You know, I'm not so opinionated on this. I mean, I still think that this saying like LiDAR provides you with depth, vision with semantics, and radar with velocities makes sense. You know, so we all know that LiDARs are extremely expensive, but on the other hand, vision is simply not robust enough from my perspective at the current point in time. So when you look at, for example, robotics conferences, right, you very, very rarely see vision-based collision avoidance systems. You know, if you look at the past, then the majority of vision-based approaches or there were way more vision-based localization approaches and vision-based SLAM approaches than vision-based collision avoidance approaches. And that's also some sort of an indication. Maybe we should invest more into collision avoidance to actually assess the state of the art, right? How robust are we, right? I mean, we all know that having a false positive or a false negative when it comes to localization is not that complicated, right? It's not that bad, but having false negatives and false positives when it comes to collision avoidance, that can be catastrophic for either for the vehicle or for people, and or for people in the vehicle, simply because the vehicle stops in the middle of nowhere all of a sudden. You know, and this is something that yeah, I think I would love to work more on this and find a student to actually figure that out, but it's extremely hard. So most of the people just want to look at these semantic images instead of like doing real navigation, right, on a vehicle with these type of approaches.
Okay, very nice. Just a last question, because I really think it will connect to other presentations that we will have, to other keynotes. Federico Andrade have asked about if it's possible to use this heat net approach on harvesting, on robots to agriculture, because it's not as difficult as autonomous driving on the street, on the road, because the maps are supposed to be a bit more static than in the roads. So maybe it's a very nice place to apply.
Yeah, I mean the heat-net stuff, that's a good question. I mean, it is mostly temperature dependent, and I think plants don't have real cooling systems, so it's probably hard to see larger temperature differences in plants.
Ground in plants.
So in agriculture, but I mean, it could be with animals, that could be the case, right? And for plants, it's difficult. And I mean, we also worked a little bit on agricultural robots, and like navigating amongst plants is also very, very challenging, and building maps, particularly because these plants grow. And I mean, there you basically want, in the end, you want to know the exact ID of a plant, right? And so a plant is basically a landmark, and once you know which plant it is, you can basically do plant-specific applications, right, of pesticides and whatsoever you need. And that is something that sounds in the very beginning very, very attractive, But then once the plants grow so big that you cannot separate them anymore, then all of a sudden you have like one huge landmark instead of 1,000 small landmarks. You know, that makes it really, really difficult.
Yeah. Okay, thank you very much, Professor. I think that's all. We are a bit low on time right now. Thank you very much.
Can I ask, Julio, can I ask a last question?
Of course, of course.
Professor. First, we have to thank you very much for your very nice talk. Since you put the last question, we will still need maps once we are able to infer them on the flight. I am thinking about a trip that I have to, I am planning to do some 8,000 kilometers from Natal to Cuenca. And I cannot do that without thinking on a planning, on a map, of course. But I wish only for you, I know, I agree, I fully agree with you that we don't need a map of the environment. We can learn that environment. So I wish for you to explain a bit about this thing that I told you now at the end. I really don't need a map to go from here to Cuenca. I can go by myself. But are we already read on technology and on the higher level systems that we would need for that, for learning and so on? Professor.
Yeah, that's an interesting question, Luis. I must say I don't have a proper answer for that, and which is good, you know. But what I think is that we still do not know what type of representations humans use in order to do their everyday task and navigate around every day. And that would be interesting, you know. That as to, I mean, that what I showed was mostly geometry, you know, that where are things, and that helps you to localize. And but you know, I once had just to give you one anecdote, I had a project about navigation in supermarkets, right? And basically to be able to, like, without a map, navigate a supermarket in a way that, and there you can easily, like, if you give the robot a shopping list, you can, from the path the robot took, actually, or the length of the path, you can easily figure out how quickly it is able to understand the structure of that supermarket. And so it's similar, like we have, like, once we go to a new supermarket, we run around a little bit randomly, although we do have some heuristics about where things are and where not. And that information is extremely hard to express for us even, right? So what is the information that we do have about buildings that allow us to properly navigate around with them? Although in the very beginning, we also get lost and we complain, but and over time we improve. And this type of capability is something that I would like to see in robots as well.
Okay, now I understand it. Thank you.
Thank you, Professor. We have another complementary question. I would just ask it, maybe, and then we can end. Do you think your recurrent approach will help to solve this question that Professor Luis asks? I mean, to building the maps on the fly.
Which approach? I didn't.
No, I mean the approach you showed, using neural networks and using LiDAR and.
I mean, in the end, let's say a human has only 2 cameras, so to say, you know, and it has some sort of odometry as well. We kind of know how many steps it took us to get from A to B. We do not know the exact distances of elements in the world, but yeah, that's basically it, right? And with that, we can navigate around. And I mean, even like if we want to have like a water, then we know where we need to go to the kitchen. We have some idea about what kitchens look like, and maybe from looking into rooms, we figure out what the kitchens are. We know where the fridge is or what a fridge is. So we have all these type of information. And the question is, like, is there any way to put this into a robot, and not in the form of a complete 3D model, to enable it to perform meaningful tasks, right? And transferring this from one environment to the next. I mean, if you truly think about household robots that you can buy in Home Depot stores, right? And once you unpack it at home, right? So you basically want to have it start immediately without creating a full-fledged 3D map that is useless after your children are messed up your living room, or so, you know.
Okay, so I think that's all. Thank you, Professor, once more. It was a very nice and interesting presentation. I invite you to come back to other presentations during the event if you have time. I know that you are busy, man. So, you are very welcome on the event on LARS this year. Thank you very much. Thank you, everyone, from the audience. Professor, if you want to say some last words, it's up to you. Thank you very much.
Yeah, thank you again for inviting me, and that I do hope that we will all be able to see each other in person in very, very soon. And I would actually have loved to come to Brazil and see that place. Must be spectacular.
Yes, I hope so. Yeah, thank you very much. Thank you. Thanks, everyone.
Thank you. Bye.
Bye. So I believe we have the lunch break right now, and we are going to have some very nice talks afterwards. Thank you, everyone. I hope to see you soon after the lunch break.